Okay, so in this question, we're told that 8 students, have taken 2 separate tests, test 1 and test 2. First one being out of 50 marks and the second one out of 30 marks. We're asked to use our calculator to find the Pmcc, the product moment correlation coefficient. So we're simply just going to type these numbers into list 1 and list 2 on our calculators, and we'll go through the normal menu system of going to calc, regression, x, a plus bx, and right there on that screen we have our r value, which is 0.7889. Also on that screen we're going to have our a value and our b value, which we'll probably use a little later on. Part B of the question asks us to explain how the value of the Pmcc is going to be affected if the individual test marks were converted into percentages. So instead of a score out of 50 and a score out of 30, how would it be affected if they were changed into percentages? Well, doing that is going to be linear coding. We're basically going to multiply test 1 by a multiplier of 2 and test 2 by a multiplier of 10 over 3. So both of these are linear coding, and linear coding has no effect on the correlation coefficient. Okay, so just making sure that you can specifically say that. Part C of the question. In part C, we're asked to test at the 1% level of significance whether there's evidence of positive correlation between X and Y. So it's a hypothesis test as always. We'll start with the null hypothesis and the alternate hypothesis. The null hypothesis is that rho equals 0, while the alternate is that rho is greater than 0. Just going to state the n value. We know there were 8 students, significance level of 1%, and the critical value I'm going to look up in the tables. And the critical value is 0.7887. Okay, let's have a spectrum of correlation coefficients from -1 through to 1. Our critical value, I'm going to mark here, 0.7887. And just remember that anything in the shaded area, anything in the shaded region is going to be significant, and we're going to reject H0. So just looking back to the Pmcc we calculated, it's very close, but it is over here in the shaded region, in the rejection region. So we do have sufficient evidence to reject H0. Okay, let's just formalize this. So 0.7889, our calculated value, our test statistic, is greater than the critical value. We have a significant result. And we can say from here that there's evidence to reject H0. We can say from here that there's evidence to reject H0. There is evidence that the better a student scores in test 1, the better we'd expect them to score in test 2. And the final part of the question here, part D, we're told that a student was absent on the day that the second test. And in the final part here, we're told that a student was absent from the second test, but he had obtained 30 marks in the first test. Can we use linear regression to estimate the student's mark in the second test? To do this, we want to just produce our regression line, for which we're going to need that A and B value that we had on our calculator summary screen. The A and B are going to be the intercept and the gradient of the regression line. So y equals a plus bx is what we're going to use, which gives us y equals 3.9617 plus 0.4622x. Okay, so now that we have this equation, we're asked to try and predict what score they will get on test 2 if their score on test 1 was 30 marks. So when x equals 30, just substitute into this and solve in your calculator. Y is going to equal 17.827. So approximately 18 marks. We could expect this student to get 18 marks in test 2.